Swayam Prabha. Digital India. Educated India.
Okay, good afternoon. So, the separation or purification of compounds can be achieved by three options we discussed. We have mass transfer operations, mechanical operation, or chemical reaction approach. So, sometimes we can have combinations one after the other. I already mentioned that in the case of drying, you could do first centrifugation followed by a drying. Okay, one after the other. In other times, you could also have combinations simultaneously. For example, when you do absorption, you can have absorption along with the reaction. The solute, when it gets transferred to the liquid phase, it can also undergo a reaction in the liquid phase. For example, CO2 absorption with the reactive solution is one example. Or if you think about distillation, you can also have a reactive distillation where while there is a separation, in one of the phases, one of the compound can actually undergo a reaction also. So, it is also possible to combine mass transfer operation along with mechanical or with the reactive systems. Okay, so those are all choices. Now, when you look at all these combinations, then we have to think about which method or which process we should select. So, this choice involves cost analysis, which methods are cheaper, and whether there is a design principle available for such methods. That is also very important. Okay, so recently we are also thinking about circular economy, sustainability, where we don't want to choose a cheaper option at the cost of environmental unfriendliness. We may have to choose eco-friendly material even though it may be costlier. So these are some new design principles that are emerging to replace some of the old mass transfer operations with more green solvents or more sustainable materials, so that we don't harm the environment. Okay, so these are the principles and ideas we should keep in mind when we think about selecting a particular process. Okay, so now we will go to let's say we want to do mass transfer operations. Okay, we will rule out the other combinations for now. Okay, for this particular course, we will deal with only mass transfer operations. So here, when we decide a particular mass transfer operations, so which way or in which manner we want to conduct this mass transfer operation also needs to be decided. Okay, so we basically have three choices. We do something called solute recovery versus fractionation. Sometimes we have to decide between unsteady process versus steady state process or operations in this case. And thirdly, we have to decide whether we want to do it in a stage wise or continuous contact mode. So these are all methods of conducting mass transfer operations. Okay, so let us look at each one of them in detail. So in the case of a solute recovery versus fractionation, let's say we have a mixture of methane, pentane and hexane. Okay, it's a gas mixture. So in this case, if you take this gas mixture and then contact this with the hydrocarbon oil, what will happen is pentane and hexane will get dissolved into the hydrocarbon oil, whereas methane will still be in the gas phase. This is because of a vast difference in the vapor pressure of methane versus the other two compounds. So in this case, we can treat this methane as a solvent like behavior, and this pentane and hexane is more like a solute. So in this particular absorption, we have recovered pentane and hexane as a solute. So this is called a solute recovery from a solvent, which is methane in this case. Okay, so in this case of similarly, other than absorption, similarly you can think about adsorption, leaching, where a particular solute is transferred or removed from a mixture. Okay, so this is something we associate as a solute recovery mode or solute recovery operation. What is fractionation? So now let's say again we'll take a liquid mixture of pentane and hexane. Okay, it's a liquid mixture, and now we want to purify this, we want to separate this. So in this case we can do what is called this distillation, where the differences in the boiling point, even though the boiling point difference may be very little, but still you can use distillation as a means to separate pentane and hexane. Okay, so this is something we call as a fractionation, because we are fractionating the mixture into rich and leaner phases of one of the compounds. Okay, so when we do mass transfer operations, we classify them as either solute recovery operations or fractionation operations. Now coming to the second choice between unsteady and steady. So in unsteady, this is relevant in the case of batch processes and semi-batch processes. So in the mass transfer equipment in which we conduct an unsteady state process, you will see the composition will be a function of time. Okay, in the entire mass transfer equipment, if you take one particular location and if you observe the composition as a function of time, you will see the composition varying with respect to time. Okay, so that is something we call it as an unsteady state process. Typically a batch and semi-batch process are such that the composition will change in time. Okay, this is one particular way of doing it. And there is this a steady state operation. So in this case there will be always mass flowing in and out continuously, mass is coming in and mass is leaving out, and then if you look at any particular location in a mass transfer equipment, you will see the composition is invariant of time. So in the steady state process, there is mass flowing in and mass flowing out of the mass transfer equipment at a steady state. Okay, and if I take any particular location inside this mass transfer operating equipment, you will see the composition in that particular location is constant. Okay, so this is something we associate as steady state operation. So we have a choice to make between whether a particular mass transfer operation to be held in a unsteady state batch process or a steady state continuous process. Okay, so that's a choice we have to make. And thirdly, about this stage wise and continuous. So what is a stage? A stage is one where we take two immiscible phases for which we want to effect the mass transfer. For example, a gas and liquid. We have an equipment in which we make them into contact, allow for sufficient time for mass transfer to take place, and then we physically separate the two phases. Okay, this particular process, that is mixing the two phases, keeping in contact for some time, and then physically separating the two, this entire operation is called a stage. Okay, so in this stage, you can have time is a factor. You can actually have longer time for contact so that more mass transfer can happen, or you can have very shorter time, and then the mass transfer will not be complete to equilibrium. Okay, so those are the choices we have to make. Now an example, if I have to say, if you want to do a leaching operation, so you take a solid and then you treat this with a, let's say, liquid, and then after certain contact time you separate the solid and the liquid, and the liquid would have the solute transferred to. Okay, now this is one stage. Sometimes we may not be able to achieve the entire separation in one single stage. So in this case we have to have a stages connected in series. Okay, so stages connected together so that if I denote this is one stage, two phases are coming here and they are allowed to contact here, and it is physically separated, and then this can go into another stage. So you can have a cascade of stages. So the connecting stages together is called cascade. So this is to ensure more contact time and better recovery. So when we think about mass transfer operations, we again have this single stage and multi-stage operations, and this is something we call as a stage wise contact. The other possibility is a continuous contact, where continuous contact. In this case, we don't physically separate the two phases. In the inlet, the two phases are allowed to mix together, and throughout the mass transfer equipment, the two phases are in continuous contact. They are only separated at the end of the operation. Okay, so that is called the continuous contact process. Typically, this happens in a packed bed kind of a system, where there is a packing and the two fluids are allowed to pass through the packing. As they go through this packing, they will have an interfacial contact between the two phases, and at the end they are physically separated and then analyzed. So this is called a continuous contact. The reason why we are distinguishing between a stage wise and continuous wise contact is because the design principles are quite different for the two. Okay, so as we are going to see further, for any particular operation like distillation or absorption, when you conduct a stage wise or a continuous wise, the design principles are different. Okay, so we have to take into account of those. So these are three different ways we have to think about conducting the mass transfer operations. So now another aspect of the mass transfer operation is design principles. So what are we really going to design? Generally, a problem was given to us. We want to separate something from something else, and mostly we know that this particular material is flowing in a particular flow rate, because mass transfer operation does not happen in isolation. It is always a part of a bigger system, right? Either the inlet of this mass transfer equipment probably is an outlet of a reactor, or the outlet of this mass transfer operation will have to go into a particular another process. So mass transfer operation always is in the center of many other processes happening. Okay, so because of this, we will know how much gas flow rate, how much liquid flow rate is actually entering, and what are the compositions and how much we want to separate. So that is a problem statement. Typically we know that. Okay, once we have that problem statement, then the design principle basically involves answering questions like, what is the number of equilibrium stages that we need to provide in the case of stage wise operations. In the case of continuous contact, what is the length of the bed, length of the continuous contactor. So for a given problem statement, we need to find out what is the number of equilibrium stages to achieve this particular separation, or in the case of continuous approach, what is the length of the packing that I have to provide to effect this particular composition change. Okay, this is one particular question we need to answer. To do this, we need to apply a material balance or mass balance, and we also would need the equilibrium behavior or the equilibrium curve. We are going to discuss more in detail about equilibrium curve. You can roughly think about equilibrium curve as one which limits the extent of mass separation. Okay, it's going to be, there's going to be a thermodynamic limit to which you can separate a compound from a mixture, and that is given by equilibrium curve, which is very specific for a given system. Along with this, material balance, which is also has to be followed. Okay, so with these two information, we will be able to find out the number of equilibrium stages or the length of the packing that we need in the case of contact, continuous contact. The second parameter or the second variable that we need to estimate is the time of contact. So how much time we need to provide to conduct this particular mass transfer operations. So in this case, we need to know in terms of stage wise operations, what we are basically saying is, what is the stage efficiency. So stage efficiency we have not defined yet, but then it basically roughly relates to whether a stage allows a complete equilibrium composition or it is falling short of equilibrium composition. How, to what extent we have achieved the mass transfer. Okay, so to calculate stage efficiency, you can increase the contact time so that the stage efficiency will go up. Okay, but again there are other constraints. If you increase the time of contact, then maybe the column will be too long or too big. Okay, and a capital wise it may not be allowed to. So you have to make a compromise. You have to make a compromise to what extent this stage efficiency can be controlled. So when I say time of contact, it is basically related to what is the stage efficiency with which we want to operate this mass transfer operation. For this, we will need, along with the material balance equilibrium curve, we will also need the mass transfer coefficients. Or in other words, the diffusion rates. The stage efficiency or the time of the contact time required are basically related to the mass transfer coefficient or the diffusion rates also. And the third thing is permissible flow rates. So in the problem statement, we may say the stream is flowing in a particular flow rate, but you use another stream to recover. For example, in the case of gas absorption, you will know how much amount of, let's say, ammonia air mixture is flowing in and what's the composition. But then as a designer, we have to decide how much amount of liquid has to be circulated to effect the required composition change. So there is a design change, so we need to design how much amount of liquid flow rate has to be used. For this case, we need pressure drop calculation. Because ideally you can say, I would like to have a maximum flow rate of liquid so that I can have better separation. But when you increase the flow rate of liquid, the pressure drop will go up. If the pressure drop goes up, then you need the mass transfer operating equipment to be much more larger in diameter, okay, but again involves capital cost. So there is a optimization that is needed so as to have sufficient amount of liquid flow rate so that you can manage the pressure drop, okay. Pressure drop again requires pumping cost and other things. So calculating the permissible flow rate means calculating pressure drop, for which we need fluid mechanics or hydrodynamics, along with material balance and also. And the fourth is energy requirement. If you consider a distillation, I mentioned that you take a liquid mixture and you vaporize it partially. So that means in this case you are going to use latent heat and sensible heat compound to heat the mixture from one temperature to other temperature. So there are heating requirements and there are also cooling requirements. So how much cost is involved in providing these temperature changes is also of considerable interest for us to calculate. The energy is not only involved in this heat addition and heat removal, but also sometimes we use a pump to deliver the liquid or gas, okay. Sometimes we want to dispense the liquid or gas. So pumping cost, fans, any other cost associated with the moving of the fluids, dispensing of the fluids, as well as heating and cooling, all this has to be budgeted out in terms of energy. So as far as the design principle is concerned, when we look at any particular mass transfer operation, we are going to ask these questions: what is the number of equilibrium stage we need to provide, or what is the time required, what is the stage efficiency we are going to operate, what is the permissible flow rate so that the pressure drop is in check, and what about the total energy budget, okay. So all these things have to be answered when you design a particular mass transfer operation, okay. So in summary, if you think about what are the concepts we need to achieve all these design principle, we could summarize to say that we need material balance, we need thermodynamics, because thermodynamics provides the equilibrium curve, fluid mechanics, this tells us about the pressure drop calculations, okay, and energy budget. So this involves some amount of heat transfer calculations also, okay. So in this course we are going to invoke certain concepts you have learned already in terms of energy balance, mass balances, chemical thermodynamics, fluid mechanics, maybe to some extent some reaction also at some point of time. Okay. So whatever you have discussed so far is very subjective matter. We have not really gone into very technical things, but this is something to kind of develop what we are actually aiming at in this particular course. Okay, we are going to look at various kind of mass transfer operations. Then once you zoom into one particular mass transfer operation, then there are things about which way to conduct the mass transfer operations and what are the essential things to calculate as a designer, right? Those are the things we will be doing. Okay, so now we will go to maybe another topic which is relevant is interface mass transfer. So what interface mean here? Interface. It's between two or more phases. Okay. So remember, when I classified mass transfer operation, I mentioned about direct contact of two immiscible phases, right? We talked about gas liquid, gas solid, liquid liquid, and liquid solid. So these are all as a bulk phases, they are not miscible. Okay. But there is going to be a solute transfer from one phase to the other phase. So that's what we mean by as interphase mass transfer. That means a solute is not only going to diffuse in the single phase, but it is going to also cross the boundary, phase boundary between the two phases and then reach the other phase's bulk. Okay. So, and we are going to deal with what are the principles that govern the interphase mass transfer of a solute. Okay. We are going to again use principles of diffusion, mass transfer, but also bring in the concept of interface between two bulk phases. So many, I think most of the mass transfer operations involve such two immiscible phases, as I mentioned already. We will also discuss few other things. For example, I already mentioned about equilibrium, which is a thermodynamic limitation of a solute transfer from one to the other. Okay. Now I am talking about two things. Mass transfer is a transport process of a solute from one phase to the other. Thermodynamics is something that tells to what extent this transfer can happen. Okay. It won't be possible to entirely change the composition from 100% to 0 or 0 to 100%. A solute cannot be completely removed from one phase to the other. Okay. It will be limited by the equilibrium distribution. So now let us look at what is this equilibrium I mean and how equilibrium curves are relevant for this mass transfer operations. For this, I am going to take an example. So I have a container and I have a movable piston and I maintain a temperature and pressure P and T. Okay. So here, let's say I have water here. And here I have ammonia plus air. Okay. So it's like a batch reactor or batch system. Okay. And one of the wall is movable so that I can maintain the pressure constant. So I start with certain amount of ammonia in water and this is brought into contact with the liquid water. Okay. So the line I have drawn here, this is the interface. Okay. Now the moment you do this, what will happen is ammonia has a finite solubility in water. Okay. Initially water was pure. Now you have made this contact between the gas mixture and liquid. So what will happen is ammonia will diffuse, cross the interface, come to liquid water. Okay. So many molecules of ammonia will diffuse and cross the interface and reach water. Okay. Now this is not the one-sided process. Once you have more and more ammonia dissolved in water, some amount of ammonia will also evaporate back. Okay. So there is some sort of a dynamical way in which molecules of ammonia will transport from gas phase to liquid phase. Once the liquid has enough amount of ammonia, then ammonia will also evaporate back to the gas phase. And when this process will keep on going, if you wait long enough, then you will see that the composition of ammonia in gas phase will reach a constant value. Similarly, ammonia concentration in the liquid phase, water phase, will also reach a constant value. Okay, so that's where we say the mass transfer has finished. Mass transfer is over now. Okay, this will happen until there is a concentration gradient within each phases. Okay, now if you look at the interface, I mean, if you macroscopically, if you look at it, you'll see the composition is constant with the time. Okay, the equilibrium is reached. But if you look at very close to the interface, you will see some molecules of ammonia getting absorbed into water, and some molecules of ammonia leaving the water surface to gas phase. There is going to be a dynamic equilibrium at a molecular level very close to the interface. However, as a macroscopically, if you look at the composition, if you measure a composition in the two phases at equilibrium, they will reach a constant value. Okay, even though I say they reach constant value, they will not be equal. Okay, so I'm making a lot of statement here. So at equilibrium, what are the things we can say? We can say, let's say if I say Y is the composition of ammonia in the gas phase, this will reach a constant value. X, which is the composition of ammonia in liquid water, will also reach a constant value. Okay, but at a very close to the interface, there will be a dynamic equilibrium between the absorption and desorption process that will keep on happening. Okay, now at equilibrium, what it means is that the chemical potential of ammonia in gas phase is actually equal to chemical potential of ammonia in the liquid phase. So if I have to write mu of gas is mu of liquid. At equilibrium, I already mentioned temperature and pressure are held constant, okay, across the two phases. The only thing that is not equal in the beginning were the composition or the concentration or the chemical potential. So once you have made the direct contact between the two immiscible phases, thermodynamics will determine the transport of the solutes until it reaches an equilibrium value. When I say equilibrium, it is a condition where the chemical potential of ammonia is equal at both in the gas phase as well as in the liquid phase. This does not mean Y will be equal to X. Okay, this is not true. Okay, we can only say chemical potential is equal, but not the concentration of the compounds in both phases. Okay, they can be different. So that is determined by how chemical potential is related to concentration, etc. Okay, so this is very important because generally when you look at single phase, if you look at single phase, for example, I have a liquid water here and I put a little bit of dye in some point, and then over time it will diffuse, and then after some time this entire solution will have an equal composition. There you can say in the entire water concentration is equal, chemical potential is equal. You can make that statement. When you look at two phases, you cannot make a statement that the concentration will be equal on both phases. Only chemical potential will be equal. Okay, so that distinction has to be made. Generally we loosely say that at equilibrium concentration in both phases are equal. That is not correct. Only chemical potentials are equal. Concentration will be different. Okay, so in fact you can write Y as some function of X. Okay, at equilibrium the liquid composition of the solute, okay, will determine what will be the composition in the Y phase. There will be a functional relationship between the two. Okay, so to see how this happens, come back to this particular problem. We have reached equilibrium. Okay, it is a batch system. Now let's say I inject a little bit more ammonia, pure ammonia in the gas phase. What will happen? So now you have changed the equilibrium composition by putting some extra ammonia. Now that extra ammonia will have to be redistributed again to the liquid. So now another new set of equilibrium will start happening. Okay, more transfer will happen, and then the system will reach another equilibrium state, in which case the composition at the gas phase and liquid phase will be different from before you injected them, because we have changed the initial composition. Okay, so if you do this experiment, imagine you have done this experiment, by doing multiple times injecting it, you can actually have a nice functional relationship between the equilibrium composition in the gas phase versus the equilibrium composition in the X phase or the liquid phase. Okay. So, this may be the one corresponding to the initial times, and you add a little bit more ammonia. Okay. So, then you would have reached somewhere here, the new equilibrium state, and then if you can continue this experiment further and further, then you get this equilibrium curve. Okay. So, this is what we call as a equilibrium curve. Right. So, it tells you when the system reaches an equilibrium, what is the composition, what is the concentration or composition of the solute in the two phases. So, that is governed by the equilibrium curve. This is very, very important for mass transfer process, because we want to reach this equilibrium state at every continuous contact or a stage wise operation, and we will see we won't be able to completely do it. Okay. We can come close to it, but not onto it. Okay. So, how far we are away from this equilibrium will determine at what rate this process is going to take place. Okay. So, equilibrium curve is very, very important in all our mass transfer operations. Now, when you look at this equilibrium curve, this is not telling everything about the equilibrium nature of this entire system, because the system contains air and water also. This functional relationship is only for ammonia. This is a solute of interest for us. So, this relationship is only for ammonia's composition in the gas phase and in liquid phase. If you imagine, water will also evaporate a little bit to the air. Okay. You can actually even think about having another equilibrium relationship for water. It will be some other function, H of X of H2O. Okay. And if you think about air or maybe nitrogen or oxygen, you can have another equilibrium relationship for air also. So, for the same system, there is a set of equilibrium relationship, but generally we do not deal with the insoluble or insoluble components. In this case, air is not so soluble in water, and water is not going to evaporate too much into air. So, we are not going to consider these compounds. We are going to look at only the more soluble compound in this case, which is ammonia. Okay. So, when you say equilibrium curve, it means you are referring to one particular solute in a particular two-phase composition, in a two-phase system. It also means that if I change the temperature of, so this everything is actually at a particular temperature. If you change the temperature, this equilibrium curve will also either shift up or down. Okay. So, there is a lot to be said about equilibrium curve. So, it is T dependent. It also depends on the chemistry of the solvent and the gas system also. Okay. So, this equilibrium curve is for ammonia, air, water mixture. Instead of water, if you take some other solvent like ethanol, the equilibrium curve will be very different. Okay. So, it is very much dependent on the chemistry of the system. What is the chemical composition of the solvent and in the gas mixture. Okay. So, another thing to say about this is you can write this in terms of mole fractions. We generally write this in terms of mole fractions, or sometimes we write in terms of partial pressures. So, are you familiar with how to get this equilibrium curve from thermodynamic calculations? Chemical in thermodynamics, have you studied this? How do we get equilibrium curve? You want to answer? Yeah. How do we get equilibrium curve? How do you calculate this? Equating chemical potentials. Okay. And how do you get chemical potentials? So, this chemical thermodynamics was done like last semester or last year? Last year. So, you may want to brush up a little bit about the phase equilibria calculations. Okay. So, you might have studied that if you want to do two-phase equilibrium like gas liquid, you take the gas phase and you write expression for chemical potential in terms of fugacities. To calculate fugacity, you will need equation of state, and the equation of state can be as simple as Van der Waals equation of state or Redlich-Kwong or Peng-Robinson. So there are variety of equation of state that we know for a given compound. Okay, you take that, from there you can get fugacity coefficients and fugacities, and then you can write in terms of chemical potential. And now when you come to liquids, liquids are condensed phases. Okay, so here the reference states are different. We call something called ideal solution. Okay, we use Raoult's law and so and so, and then we write excess Gibbs free energy for liquid mixtures. Okay, and from there you will calculate what is the chemical potential of a compound in a liquid solution. Okay, so now the chemical potential of a solute in the gas phase is written in terms of its composition, Y. In the liquid phase, it is again through excess Gibbs molar free energy, you would write chemical potential in terms of liquid phase composition. Okay, so then you match the chemical potential and you will get a functional relationship relating Y in terms of X. Okay, this is how you would actually arrive at equilibrium curve. Okay, in this particular course I will not teach much about how to obtain this, because something you should know. We will take this as a data. Okay, whenever we do mass transfer calculation, we will say my equilibrium curve Y is equal to 2x. Okay, so this something will be given to you as if it is known to you how you will calculate. It can be done experimentally or it can be done theoretically by equating chemical potentials, pressure and temperature. Okay, so I kind of urge you to refresh your notes of chemical engineering thermodynamics to see how this is to be done. Okay, similarly, the another thing is of importance is fluid mechanics. So you might have studied flow through packed bed, right? Flow through packed beds, Ergen equations. No? Fluid and particle mechanics was done, right? So how do you calculate pressure drop of fluid flowing through a pipe, hollow pipe? How do you calculate this? When a fluid is flowing through a pipe, you do expect a pressure drop, right? The pressure will not be same at the entry and the exit because of skin friction, right? So you want to calculate that. How do you calculate? Any equation, any formula, any theory, any model? Huh? Hagen-Poiseuille, very good. Hagen-Poiseuille for laminar flow. Turbulent flow, what will you do? You will have correlations, right? Friction factors as a function of Reynolds number. There are charts. You can read up friction coefficients, and from there you can get pressure drop, right? So this is for a simple pipe. But now, if I have a packing, okay, the fluid is not flowing freely. It's going to have a lot of resistance to flow because it is packed. Why we need packing? Because we want to have good contact between the liquid and gas, because two fluids are flowing. Sometimes we actually make them flow in opposite directions, like counter current, so that you can have good mixing. But the fluid will have a lot of resistance. The pressure drop will actually go up. Okay, so it's important that you know how to calculate pressure drop of a packed column. In fluid mechanics, you should have, or you must have studied, if you have a single fluid flowing through a packed bed, how to calculate pressure drop. Very famous equation, Ergen equation, is used for calculating pressure drop. Our systems are going to be far more complicated because you have a packing, you have two fluids going opposite in each other, and when you do that, there is a mass transfer happening and the flow rates will also change. So we have all kind of complexity involved. So in this kind of problems, we don't have a hope of calculating analytically the pressure drop. We often depend on empirical correlations, charts. People have done hydrodynamic flows on packed beds and they measure pressure drop as a function of gas flow, gas velocity and liquid velocity. When you change the packing type, your pressure drop curves also changes. So please go back and in fluid mechanics course, whatever you have studied about flow through packed bed, you have to refresh that ideas also. So these are the two things you need to know a priori, because in this course we will talk more about mass transfer only. I will assume that you know thermodynamics, you know fluid mechanics. Reaction engineering we are not going to deal much, but these are requirements we need to do. Okay, And again, material balance, energy balance, something is done in chemical process calculations. Am I right? You are aware of that as well? Okay. So, different kinds of contacts, co-current, counter-current, cross-flow. In such a cases, whenever there is a change of composition, you should know how to write mass balance. So, these are very important elements. If you want to follow the lectures, it's important that you understand these three concepts. Okay. Material balance, energy balances. Energy balance not too much, but to some extent, but definitely mass balance and fluid mechanics of flow through packed beds, and then VLE, LLE calculation of thermodynamics. So, okay. So, these things you should be aware of. Okay. So, I will stop here and I will talk more about the diffusion. I mean, I will talk about a little bit about mass transfer in a homogeneous phase through the interface, how to relate mass transfer coefficient and so on, so in the subsequent classes. Yeah.